Hello AP Calculus. We are jumping ahead to lesson 2.4 from section 2.4 in the textbook. As always, read the section to get a complete understanding of what we're talking about here. It's not all going to come out from me in this video. I just wanted to go through as many of the odds as possible to kind of see like, okay, can we make connections by just doing some examples and then getting those concepts to be completely concretely implanted in your brains? Yeah? Okay, I'm going to stop talking for a second about jibber jabber and go directly to section 2.4 in the textbook. We're on page 76. This is basically doing a limit from the left, limit from the right, and the limit at a particular spot, but we're talking about rational functions now. Functions that may have asymptotes, yeah? Both horizontal and vertical. So we're gonna study this a little bit with graphs, but find a way where we can do this without graphs. So for number one, there's an asymptote at positive 4. And then when we think about the behavior of this function, all we got to do is plug in a few points from the left and from the right. And, just plugging in x equals 0, you find that 5 over negative 4, which is negative 1.25, is probably very telling of like where these functions are going to exist. Because, I don't know if you guys remembered, but there's a horizontal asymptote, and there are some rules here based on the biggest power. So the biggest power is x on the bottom. On the top, it's sort of like there's this x to the 0 power, all right, because there is no x up there, which means the bottom is bigger than the top. The rule for horizontal asymptotes in this case is that 0, y equals 0 is a horizontal asymptote. So for this function, y equals 0 is a horizontal asymptote. X equals 4 is a vertical asymptote. Which means that our graph is going to kind of follow this particular pattern. Again, I could plug in some points, but it's ultimately going to be a curve that looks very similar to that. And then on the flip side, it's going to look kind of like this on the other side. And I use kind of very loosely, like the points aren't going to match up exactly with how I graphed it. But this is super helpful for us because, you guys are pretty solid when you have the graph in front of you to say, hey, what does the limit as x approaches 4 from the left look like on this? Well, I'm just following the curve from the left, and it's going all the way down to negative infinity. So part A is negative infinity. In fact, they tell you that it's either going to be positive infinity, negative infinity, or does not exist. It's kind of just like a matching game in this case. Or from the right goes to positive infinity. And anytime you get an asymptote like this, like the limit just does not exist at that spot. By the way, I was very happy to see that the textbook writer Swakowski used DNE, and I use DNE as well, and probably every other calc teacher, so it's not really that big of a deal. All right, that's number one. Okay? By the way, there are some computational techniques with this that I'm not going to talk about in this section, but maybe you guys are starting to, light bulbs are going off. You remember, when it was from the left, it seems to be that that's the component we always use. From the right, that's the component we always use. All right, number 3 is slightly different because it's cubed here. All right? It still means we have a horizontal asymptote at y equals 0. But you know what? Maybe this is the good spot to bring out the computational technique. So if you think about it, 1 over 2x plus 5, all right? It's basically happening 3 times when it's cubed. And this whole thing's being multiplied by 8. So it's kind of like you've got 4 limits to compute. The limit as x approaches -5/2 of 8, and then of these 3 parts multiplied together. Now the rule is, the limit as x approaches a from the left of a function who all it has is a 1 up top and a variable expression that yields the domain issue. So in this case, the variable expression that yields the domain issue is 2x plus 5. Usually you guys would see it as x minus a, but here's the thing. I could have called this x plus 5/2, which is like x minus -5/2. It fits the bill for this. And you guys saw this last year during remote learning. We said that when you can separate, when you can break down, decompose a function into different parts like this, then all you got to do is say, every time this gets isolated, it's -infinity from the left. If you can get a 1 up top and create this type of structure in the bottom, it's always -infinity from the left. So it's like saying you've got 8 times that gives you -infinity, because we're talking about a from the left here. Sorry if I wasn't clear on this. This is 3a. So it's times -infinity times -infinity times -infinity, which is going to be +infinity times -infinity times 8. Ultimately, letter A computes out to be -infinity. All right? That's A. B, from the right of 1 divided by the variable expression whose 0 is the limit, okay? See, like, the variable expression was 2x plus 5. You set it equal to 0, -5/2 is what you get. The variable expression whose 0 is the limit is going to equal +infinity from the right. So, instead of this business, for part B, it's 8 times +infinity times +infinity times +infinity. Turns out to be infinity. All right, the left doesn't match with the right, but technically you're not going to have a limit existing if it is an asymptote. So part C does not exist. All right, check out number 5. Hopefully we're getting a rhythm for how the logic is breaking down here, or put together. Number 5. I'm going to take f of x equals 3x over x plus 8 squared and decompose it into 3 parts. Part 1, 3x. I'm thinking of it as like 3x over 1. Part 2, 1 over x plus 8. And then the part 3 is just another one of these. The limit is approaching -8 from the left for part A. So for A, I am plugging in -8 for any x value that doesn't have a domain issue. So I'm going 3 times -8 here. Okay? Then I'm using from the left, that formula of it's got to be negative infinity for this part. And then same thing for this one. That gives you negative 24 times a negative infinity times a negative infinity would yield a positive infinite value. But you're multiplying by negative 24. Yeah. And by the way, guys, I guess I'm being a little informal about this. Your textbook's probably going to give you a lot of different formulas that have been proven where you don't have to do kind of fake calculations. For all intents and purposes, I can't take negative infinity times anything. I know kind of the sign of what's happening and how it progresses as you keep moving outward towards infinity. I know that this value is going to be approaching negative infinity, but I can't just randomly say multiply infinity times infinity. This is very informal, I guess is what I'm saying. Part B. Do the exact same thing, except it's going to be positive infinity times positive infinity there. So it'd be 3 times negative 8. That now is positive infinity, which is interesting because it's still negative 24 times positive infinity. Still negative infinity. Now, you know what? I am going to check the textbook on this because there are some textbooks that kind of say if it's negative infinity from the left and negative infinity from the right, that at that point it is negative infinity. I don't agree with that, but I want to see what's going on here. So let's make sure that Swakowski and me and you guys are on the same page. Oh no. Well, it appears as if we're trying to say that at A, it is negative infinity. And I get where he's coming from on this. But they're not converging to a specific value. So I'm going to have to just disagree and say it does not exist. Number 7. All right, so interesting. Factor this expression. This is going to be x minus 2 times x plus 1. The domain issue is contained right here, the place where we have a vertical asymptote. So what I can do is I can separate this into 1 over x plus 1 times 2x squared over x minus 2. This is a perfectly legitimate rational expression in which I can plug in a negative 1. So when I do both of these parts from the left and from the right, this number is going to be the same every time. So for part A, plug in a negative 1, it gives you negative 1 squared times 2. That's 2. Divided by negative 1 minus 2, negative 3. 2 over negative 3. So it's negative 2/3. From the left, we use negative infinity. From the right, again, same expression, same plugging in of negative 1. Positive infinity. So A is positive infinity, negative times a negative. Left is negative infinity. And then Mr. Earl and I can agree that this would be does not exist. All right. I'll do the last one, then we'll start a new video. Number 9. You can break this up into 1 over x times 1 over x minus 3 times 1 over x minus 3. It seems like the squares have made them both either go to negative infinity or both go to positive infinity. I wonder if that's going to happen here. Well, we're going to 3, okay? So 3 is the domain issue here. So I can plug in 3 here. From the left, it's going to be negative infinity times negative infinity. From the right, it's going to be positive infinity times positive infinity. They both end up yielding a positive value, negative times a negative. So it's positive infinity for number 9 from the left, positive infinity, number 9 from the right. And I guess, I guess we can agree that does not exist is a logical conclusion. But also I can see possibly that the value that infinity is happening here is going to be the same value on the other side. It's kind of like cars that are driving parallel that are always in the same spot. They're going the same speed. So I don't know. Maybe that's the okay for saying it's positive infinity. So, I kind of want to keep it with that idea as a definition for limits existing. But just recognize that there are some very, very people way smarter than me who are going with the positive infinity.